Welcome to AP Chemistry. We'd suggest you leave now. If not, this is the Unit 1 review video. Our first topic is gram formula mass, or GFM, something you should definitely remember from your Regents or Honors days. The GFM is the mass of 1 mole of a substance. Hopefully you recall what a mole is. To find the GFM of a compound, you add up the atomic masses of every single element in that compound. You find these masses in your reference tables. The units for GFM are grams per mole. Traditionally, you round to the nearest hundredth. Pay attention to subscripts when you're calculating the GFM. We have 2 examples for you at the bottom. Why don't you pause the video and try them? Okay, so now that you've paused the video and tried them, here are the answers. Our next topic is balancing equations. This is another topic that involves moles. You have to balance a chemical equation to do any calculations involving mole ratios to find out how much is produced. And by the law of conservation of mass, every chemical equation must be balanced. So if you look at this equation here, try to balance it. And if you look in the middle of this slide, you see the balanced equation. So the mole ratio. Coefficients in a balanced chemical equation can be used to determine the relative number of moles of a compound involved in a chemical reaction. This topic is very important when determining how much product you can create or how much reactant you need to create a specific amount of product in a reaction. So if you look at the bottom, we have an example. If 10 grams of hydrogen gas are reacted with an excess amount of nitrogen, how many moles of ammonia are yielded? And here's the solution. So the first thing you have to do is convert the grams of hydrogen to the moles of hydrogen by dividing by the GFM. From looking at the balanced equation, we can determine that the mole ratio between hydrogen gas and ammonia is 3 to 2 from the balanced equation. So 3 moles of hydrogen for every 2 moles of NH3 gives you is equal to 5 moles of hydrogen for every x moles of NH3. And you solve for x and you get 10/3 mole of ammonia. So now we're moving on to molarity. Molarity is a measure of the concentration of a solution. Molarity is calculated by dividing the number of moles you have of solute by the liters you have of solution. In order to create a solution with a specific molarity, you need to be able to freely convert between mass and moles in order to make a solution, because you cannot directly measure moles. So for our first sample problem, how would you make a 50 milliliter solution of 2 molar potassium iodide solution? So give that a shot. And here is the beginning of your solution. So the first thing you need to do is figure out how much solid is needed for the solution. For a 50 milliliter 2 molar potassium iodide solution, you calculate that by using the molarity formula. 2 molar is equal to some number of moles divided by 0.05 liters. Remember to use liters and not milliliters, as that is the formula. So we determine that the moles of potassium iodide that you need are 0.1. Once you have this calculated, you can convert to grams to measure out the proper amount of solid, using the gram formula mass of potassium iodide. The gram formula mass of potassium iodide is 166.00 grams per mole. So you multiply 0.1 moles of potassium iodide by 166.00 grams per mole to get 16.6 grams of potassium iodide. To physically make the solution, use a correctly sized volumetric flask, in this case 50 milliliters. Add 16.6 grams of potassium iodide to the volumetric flask, and then fill the flask with water and mix thoroughly. If you do not need to be this accurate, you can use a graduated cylinder. Remember to put the solid in first. Dilutions are used in lab procedures when it's necessary to take a concentrated or stock solution and make a diluted or less concentrated solution. The formula for creating a dilution is M1V1 equals M2V2, when M is molarity and V is volume. Note that the unit for volume does not matter as long as it is the same on both sides of the equation. If you're using milliliters on the left, you must use milliliters on the right. So here are your steps for making a dilution. So your stock solution, you have 100 milliliters of 3.0 molar hydrochloric acid solution. Your dilution that you want to create is 75 milliliters of a 2.0 molar hydrochloric acid solution. You solve for V1 in this problem to figure out how much stock solution you will use and how much water you will have to add. So in M1V1 equals M2V2, you plug in 3 molar for M1, X for V2, 2 molar for M2, and 75 milliliters for V2. By solving for X, you find that you need 50 milliliters of the 3.0 molar hydrochloric acid stock solution. You then add 25 milliliters of water and mix thoroughly to get your final desired solution.
Significant figures. This is a topic most of you should remember from Regents and Honors Chemistry. Sig figs are very important during lab calculations so that you give answers that are up to code with the accuracy of the lab equipment that you are using. When reading lab equipment, it's very important that you must estimate the last decimal place of your answer in order to be accurate as possible. For example, if you look at the graduated cylinder to the right, because it is accurate to the ones place, you must estimate the final place of your answer and go to the 10th place. If you're at a graduated cylinder that is accurate to the 10th place, you must give your answer up to the 100th place. When counting significant figures, there are a lot of rules. If our explanation isn't as thorough as you would like, page 14 in your textbook has slightly more information. When counting sig figs, non-zero integers are always significant. Zeros are not quite as easy. Leading zeros that precede all non-zero digits don't count as sig figs. If you look inside the parentheses, 0.00001 only has one sig fig. Zeros between integers are significant. For example, the number 101 has 3 sig figs. Zeros trailing at the end of numbers depend whether or not there is a decimal point. 1000 only has 1 sig fig. However, if there's a decimal point at the end, it has 4. 1000.0 has 5 sig figs. Exact numbers. These numbers are assumed to have an infinite number of sig figs and won't limit the number of sig figs in your final answer. These numbers include constants like the 2 in 2 pi r, or the 4 in 4/3 pi r cubed. Also, numbers derived from counting are exact numbers. If there are 8 molecules or if there are 3 apples, those numbers are assumed to have infinite number of sig figs and won't impact your calculations. Calculations with significant figures. Addition and subtraction. The final answer has the same number of decimal places as the least precise measurement. If you look at the example problem, we have 23.49 plus 1.3. If you look at both numbers being added together, 1.3 is the least precise measurement because it has the fewest decimal places. Therefore, your final answer can only be reported to 1 decimal place because 1.3 only has 1 decimal place. This means you have to round your answer of 24.79 to 24.8. Multiplication and division. The rule is the final answer has the same total sig figs as the measurement with the least number of sig figs. If you look at the example problem, we have 8.6 multiplied with 9.859. Because 8.6 is the least precise measurement because it only has 2 sig figs, your final answer can only have 2 sig figs. This means you have to round your actual answer of 84.7874 to 85. Naming. Naming compounds and going from the molecular formulas to the name of a compound is an important tool that you're going to need all year in AP Chemistry. This slide is going to be a general outline going from the molecular or empirical formula to the name of the compound. Your first step is going to be to look and see if the first element listed is a metal or a nonmetal. If the first element is a metal and has more than one positive oxidation state, like most transition metals, you're going to need a Roman numeral after the name of that element telling us what charge it has. For example, iron is an element that's a transition metal that has multiple oxidation states. +2 and +3 are very common. In order to name a compound using iron, you're going to have to use Roman numerals to tell us what oxidation state iron is currently in. If your first element is a nonmetal, use the prefix naming system with prefixes like mono, di, tri, and tetra to tell us how many of that element exist in the compound. For your second element in your compound, you're going to change the ending of the element to "ide," unless it's a polyatomic ion, in which case you shouldn't change the name of the ion at all. The AP reference table, unlike your honors or Regents reference table, doesn't have the names of common polyatomic ions, nor does it have oxidation states for elements. So I suggest if you aren't well versed in these areas, you find a Regents reference table and review. You guys are really going to need to have this memorized for the entire year, so it's a good thing to start off early. These are a few examples of some formulas that you guys should pause the video and try to see if you can come up with the names. Okay, so now that you guys paused the video and tried these problems, we're going to go through the answers. The first compound is probably the easiest answer. It's just going to be potassium iodide. Potassium is a metal, but it only has one oxidation state, so you can keep its name as is. And the second element in the compound is iodine, and you're just going to change that to iodide. The second answer is a little harder. Because iron has multiple oxidation states, you're going to have to signify which oxidation state it's in with the Roman numeral 3. And the way that you know it's a +3 oxidation state is because all compounds have to be neutral, and because chlorine has a -1 charge, and there's 3 of those, you know that iron has to have a +3 charge to make the compound neutral. The next one is even harder. Ammonium and cyanide are both polyatomic ions located in the Regents reference table, but not the honors, so you're going to keep those names as is when naming the compound. The last one, because phosphorus is your first element and it's not a metal, you can use the prefix naming system, and because there are 2 phosphorus and 5 oxygen, it would be diphosphorus pentaoxide. The next slide is naming techniques going from the name of the compound to the chemical formula. In order to do this, you're going to have to look up the symbols for elements and polyatomic ions, which, as I said, aren't on the AP reference table. And for polyatomic ions, it's also important that you know the charges. To determine the charges of the elements and ions in the compound, you're going to have to crisscross and determine the coefficients to make a neutral compound. However, if the name uses prefixes, the prefixes straight up tell you the coefficients for elements and ions. Roman numerals also will do the same. These are a few naming examples from going from the name of the compound, and you guys should pause the video and see if you can write out the formula. Okay, now that you guys tried those, we're going to look at the first one, which is dihydrogen monoxide. Because this uses the prefix naming system, we know that there's 2 hydrogen and only 1 oxygen, and that's going to give you H2O or water. Your second example is sodium carbonate. Carbonate is a common polyatomic ion with a -2 charge. So in order to make this a neutral compound, you have to crisscross and give sodium a subscript of a 2, which will give you Na2CO3. Your last example is lead-2 nitrate. Nitrate is another common polyatomic ion with a -1 charge. The Roman numeral 2 signifies that lead has a +2 charge in this compound, so in order to give the compound a neutral charge state, the NO3 entire polyatomic ion has to have a 2 subscript. Solubility. Solubility is something that you guys are going to work with all year, and it's a quantitative term determining how well a solute dissolves in a particular solvent. The substance dissolving in the chemical in question is referred to as the solute, and usually the liquid that you're dissolving either a solid or a liquid in is referred to as the solvent. Solubility rules, unlike in honors and Regents chemistry, cannot be found on the reference table, so this is another thing you guys are going to want to memorize, and we're going to take a look at the chart on the next slide. It's not necessarily required or even necessary to memorize the entire table, but you guys definitely should know a few very common rules. Group 1 ions, the fact that those are always soluble is something important to know, as well as very common polyatomic ions such as nitrates and carbonates come up a lot in labs throughout the year. Again, this is something not on your AP reference table, so in order to get this information and study it, you're going to have to look up a Regents reference table. It's the end of our video. Have a great year in AP Chem. Good luck.
You'll need it.
It's pretty difficult.